Okay, this is part 2 of the solutions to your test. Starting at question 13, here we have the question. You have to draw a circuit diagram, calculate time constant, and then sketch a VT graph for the discharge over a time of 4 minutes. That was the end of the last test, was it? Was it? Yeah, this test started on 13. Okay, here's my circuit diagram. As long as you've got the 3 components in series and the voltmeter in parallel, I'm saying that 1 mark for them in series, 1 mark for it in parallel. Doesn't matter on the order, doesn't matter on the rotation, etc. That's part A. Part B, take the formula from the formula book, put in R, put in C, get an answer of 100 seconds. That's a 1 mark question, so just the 1 mark for that. This one kind of, that's the shape of the graph. Don't do what I did initially and not get them connecting. I think that's important. So I've said that the first mark is for starting T0 at V equals 12. I've said the second mark for the general shape of the graph, an exponential decay curve. And then I've said the third mark for making some form of calculations. You know where the half-lives are because you counted it in part B. Calculated it in part B. And then I've used a formula from the formula book here. Gone through it. V0 is the 12. T, I've gone for half-life, so 100 seconds. And we know that the time constant is 100. So I've said that V equals 12e to the minus 1, which is 4.4 volts. Did it again for 200 seconds, and then sort of sketch them on the graph there. And you have to do it up to 4 minutes, which is 240 seconds. So you're only expected to do somewhere around here. I figure as long as you've got one of those annotated on, you're probably good for the third mark. Next question then is this one about magnetic flux and induced EMF, etc. Define magnetic flux on the next page. So this I've defined using the formula. There it is. And then I've for 1 mark, and then I've explained what the symbols represent for the second mark. I looked this up to see whether there was another definition. So I found a different question on the IB question bank where you had to define magnetic flux, and they said that magnetic flux density, field strength, normal to the surface times the surface area. They're just saying the equation in words essentially, but it says allow fully explained equation or diagram. So a fully explained equation here, I don't think you get away with a diagram in our question because there is one. Part B, a thin copper ring encloses blah 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 blah. Calculate the EMF induced in the ring. So I said EMF is a rate of change of flux, so it's BA over time. In the question, they tell you that the rate of change of field strength is 5 times 10 to the minus 2. So that's essentially B over T. So we're just doing B over T multiplied by A, and we get 9 times 10 to the minus 5 volts. So I've said 1 mark for the first statement, rate of change of flux, and another mark for a calculation that leads to 9. I guess if you've got 9 times 10 to the minus 5, you've got all the marks, you've got both marks. Next part, question 15, sorry, not next part, next question. Learn how to operate your laptop, Bill. Here we go, circuit diagram, standard, very common question. Calculate the EMF in the cell. So first part, EMF is energy over charge. There's the numbers, they give you that in the formula, and I get 1.4 volts. Again, if you've got 1.4 volts, you've got the 2 marks. but I'm saying there's a mark for the equation as well. Part 2 is you have to find the internal resistance of the cell. So we know that EMF generated is split between the potential difference of this and the potential difference of this. So we have that standard equation. The EMF is the potential difference of the outer circuit plus the internal voltage or internal potential difference lost. Rearranged, EMF is V plus IR. You do all sorts of this. You might remember this lesson where we then swap that for big I, big R, and then take out the I's and do big I brackets big R plus little r. There's all sorts of connotations of this equation, but this is a fairly common one. This is the graphical one as well if you do the graphical method. So I've said a mark for stating that equation, a mark for doing V equals IR just for the outer part of the circuit, the 12 volts, 1.2 volts and the 6 ohm resistor, and get 0.2 amps in the outer part of the circuit. Current doesn't change, so that's the same throughout. So then put the numbers of 1.4 as the EMF, 1.2 as the, and then get ourselves an answer of, you would have an error carried forward here. If you got that wrong, but you used it here correctly to get a different answer, then you would get error carried forwards. All of the marks for this question would be untouched. You'd have already been penalised in that one. I get resistance of 1.0 ohms for the internal resistance. Then the last part was to calculate energy transferred in the resistor R. I said it's just a ratio, so 1.2 volts out of the total 1.4 is an amount of energy out of the total energy. And then I rearrange that equation to give me 6.9 times 10 to the 3 joules. Remember the times 10 to the 3 joules. And then the last question, it is the last question, isn't it? 16. State Faraday's law of electromagnetic induction. You should just be learning that and then use it to explain why the transformer must have AC. We did that in class. Explain why it's laminated. You just need to learn that. That comes up very regularly actually whenever this question appears. So just learn it. There's 2 common ones, and then you have to do some calculations. So Faraday's law, the EMF induced in a coil is proportional, that's worth a mark, to the rate of change of flux. I said flux linkage in the circuit, but then I looked it up and it doesn't need that final bit. So EMF is proportional, I said is 1 mark, to the rate of change of flux. I said there's 2 marks. I guess if you're talking about rate of change of flux, you've probably got both marks. Then part BI, you have to explain it with relation to why you need an alternating current. Yeah, explain why for not the current in the primary must vary continuously. Yeah, you're basically saying why do we need an AC current to make it work? Well, for an EMF to be induced, flux must be changing, worth 1 mark. Therefore, current must be changing in the primary coils. And that's the 2nd mark. Stock answers to why you laminate a core. Minimise eddy currents within it and minimise energy loss. Just learn those 2. They're just simple recall of information. Then the last one, you have to calculate number of turns. So this is a formula. I think it's in the formula book. We have everything except 1, so we can rearrange it and get an answer. And then P equals IV, I equals P over V, 42 watts over 230 volts. They tell you that in the question, 0.18 amps. I guess if you put that and you've put that, you've got all 3 marks, but I said the 3rd mark could be just given for that formula. So if all you've managed to do is correctly state that formula, then you've got a mark. I don't think stating P equals IV is worthy of anything within the diploma programme. It's not worth a mark in GCSE, so why would it be in DP? Yeah, that's it.